We'll now talk about the first kind of deep generative models, which are perhaps arguably the most popular deep generative model too, which is Generative Adversarial Networks or GANs. The question that we left behind from the last lecture was, why does using KL divergence in finding the generative model simplify to maximum likelihood estimation? If you recall the problem was theta star is argmin over all thetas from a family of distributions M, some distance function of p theta from PD, and if this distance is KL divergence, remember the definition of KL divergence is if you had two probability distributions P and Q for simplicity, this is given by P log P by Q. That's the formal definition of KL divergence to recall. So in this case, you would have the KL divergence of PD and P theta. So the first term PD does not depend on theta, so it doesn't matter for our optimization. So you're left with log PD by P theta, which can be written out as log PD minus log P theta. Once again here, log PD is the distribution of data and does not depend on theta. So you're left with argmin over theta, expectation over all the data samples from your distribution PD minus log P theta of X. And this is maximum likelihood estimation or minimizing negative log likelihood. So a fairly trivial thing to show as we mentioned the last time. Let's recap some of the concepts that we spoke about in the last lecture. We said that generative models try to learn a probability density function P of X over a given set of images training data X. And if you knew the distribution, if that was parameterized as a Gaussian, P of X assigns a positive number to each possible image depending on its probability of being generated by that distribution. It tells us how likely that image X is under that distribution P of X. And we said that applications of generative models include sampling and generating new data, likelihood estimation, which could help you in outlier detection because you have a certain distribution and you have a certain likelihood of a data point belonging to a distribution. If that likelihood is very low, it's likely that the point was an outlier. Similarly, you can also do feature learning, which we'll talk about more in this lecture. We also talked about last lecture on density estimation of the probability distribution from an implicit perspective and an explicit perspective. These also define the different approaches for deep generative models. In explicit density estimation methods, you try to write an explicit function for the probability distribution. For example, you may say P of X is equal to f of x theta, where f could be a Gaussian function in the case in which you assumed a Gaussian distribution for the density. In this case, the input would be image X, the output P of X would be the likelihood value for image X, and the parameters would be the weights theta, which defines that function that you've assigned for the density. So in this case, an explicit likelihood is assigned for each image, and with explicit density estimation approaches, one thing that you will realize as you see different methods is they are very good at outlier detection for the same reason that we just said. So if a point's likelihood of belonging to a distribution is very low, it is perhaps an outlier. But explicit density estimation approaches do struggle to generate images of very high quality. sometimes can also be slow in generating images. On the other hand, implicit density estimation approaches do not try to assign a functional form to P of X. Instead, they only aim to ensure that given a model, you can sample images from that model without worrying about an explicit likelihood assignment for each such sample. So that's not part of the model. And it happens that such methods end up providing avenues for better sample generation and faster sampling speed. With that recap, let's move on to the focus of this lecture, which is generative adversarial networks. These networks were developed in 2014 by Goodfellow et al. The goal of GANs is to build a good sampler that allows to draw high quality samples from P model of X, where P model of X defines samples that are drawn from a model which is learned through this algorithm. As we just mentioned, there is no explicit computation of a certain functional form for P of X. The only objective we have is to ensure that whatever images we sample from the model, the distribution of those samples, which we call P model of X, remember, we are not going to assign any likelihood value for P model of X. All we want to ensure that if you collected a set of samples from that model, that distribution of samples should look similar to your original data distribution. There's no likelihood assignment for each sample. So we ideally want the output samples to be similar but not exactly the same as your training data. Why do we say that? Because if we have the same samples as training data, firstly, the neural network is perhaps memorizing and not really learning much. Secondly, you perhaps then don't need such a model. You only need a model which can then generate diverse samples beyond what you already have. So how do you achieve this goal? So the key idea in generative adversarial networks or GANs is to introduce a latent variable Z. So this is the latent variable with a simple prior, for example, a Gaussian prior. And once you sample from that random variable, from that Gaussian, you pass it through a module called a generator. In our case, a generator could be a neural network. And you give an input to that generator neural network, and the network outputs an image. So this module is known to us from whatever we've seen so far. We've seen semantic segmentation methods where the output layer is the size of an image itself. Similarly, here also the output of the generator would be an image itself, and that's what we define as the distribution coming out of the generator. Let's call that X hat. Those are the samples coming from PG. PG denotes the distribution of images generated by the generator G. Now, what do we want? We want to ensure that if we had a distribution of training data given by P data, we want to ensure that the distribution PG must be close to P data. Observe that we are not trying to assign a likelihood to every data point X hat or even X for that matter. We want that distribution PG to be close to the distribution P data. The challenge on implementing this, we are not imposing any particular parameterization on PG or P data. So we have to find a way to find the equivalence or to ensure that PG becomes close to P data without knowing what kind of a distribution it is. Remember here, the Gaussian is only an input vector. We are not assuming any Gaussian or any parameterization on your P data and PG distributions. So how do we go about ensuring that PG is more or less close to P of data? To do this, the originators of this particular method, Goodfellow et al., had an interesting idea. They introduced a classifier called a discriminator, which we'll denote as D in this lecture, to differentiate between real samples and generated samples. So if data came from P data, it would be given class 1, and if data came from the generated distribution, that is exact coming from PG, then it would give a class 0 for that image. How does this benefit? Our goal is to now train the generator to ensure that the discriminator misclassifies the generated sample x hat into class 1 and can no more differentiate between the original distribution P data and the new distribution PG. So the way we are going to equate PG and P data is through this discriminator, which the generator will seek to confuse. The job of the discriminator is to separate the fake or the generated samples. By fake samples, we mean the generated samples from the real samples, and the job of the generator is to fool the discriminator. So you can also consider this like a cop and thief game, where discriminator is like a cop that can separate real and fake, and the job of the generator is to fool the discriminator. That's the overall idea. How do you train such a generator or a discriminator? So the training objective for GANs is given by it's a min-max optimization problem. You minimize over G, which are the parameters of your generator network. You maximize over D, which are the parameters of your discriminator or the classifier network. Expectation of data coming from the real distribution, log of D of x. Why is this correct? We are saying that for points that come from your original training distribution, we'd like the discriminator to maximize the log likelihood of those data points. And the second part states, if you now take a sample from the Gaussian and give that Gaussian to your generator G, and the output of the generator is given to the discriminator, we want to ensure that the output of that is 0. At least the discriminator must aim to make this value 0, and that would happen when this entire quantity is maximized. But on the other hand, the generator's job is to ensure that this last quantity goes to 1, which would minimize this entire quantity, and that's why you minimize over G and maximize over D. This also is intuitive because generator and discriminator are playing a cop and thief game, and each would like to outwit the other. So while the discriminator wants to maximize terms in the objective, the generator wants to minimize corresponding terms in the objective. So such a min-max problem is also known as a zero-sum game. This has origins in game theory, which we will not get into now. And we assume that the discriminator has a sigmoid activation at its output layer. Remember, the discriminator, at least in this particular example that we are talking about, is a binary classifier. It only has to say real or fake. So the best activation function that you can have in the output layer of a binary classifier is the sigmoid activation. We now assume that a discriminator has a sigmoid activation function in its output layer. So let's try to parse this objective function a bit differently. If you look at the first term here, if you look at this part of the term, let's write that and call it objective 1. So objective 1 states that we'd like to train the discriminator such that if sample belongs to P data, which is the true training data distribution, we maximize the log probability of it being a real sample. And the second part is objective 2, which talks about minimizing the generator with respect to the second term. Remember that the first term does not have anything to do with G, and hence in the minimization of G, the first term does not matter and can be excluded. So while minimizing G, what are we looking for? We are looking to train the generator G such that if sample belongs to PG, that is its output of the generator G, we'd like to maximize the log probability of it being a real sample. That's what the generator would like to do, although the discriminator would also like to maximize this quantity. What do we mean by expectation in these two terms? In practical implementation parlance, the expectation simply means that the losses are averaged over a batch of samples. What does a batch of samples mean here? We'll see that in a moment when we see the algorithm. Now coming to the training strategy. So the first thing that you can think of is now you have two networks to train, D and G. So far we have seen several other approaches where we had two networks to train. We had detection with two heads. We talked about a Siamese network with two branches. We talked about a two-stream CNN with two branches. But in all of those examples, both branches were trained with the same loss or the same objective. Largely speaking, we had examples like triplet loss where things slightly changed, but otherwise it was the same loss. You minimized the same quantity across the complete network to a large extent. So what can we do here? One option is we can train D completely first, so we have a good discriminator, and that can be done by optimizing only the first part of the objective, O1, and once we have that, we can train G to optimize O2. Does that work? Does that have any problems? Let's try to think this through. If D is initially very confident, which means you have trained an excellent discriminator or a classifier, then it would be able to say that any sample that comes from G is a fake. So which means if you get an X that's obtained from G or corresponding to the distribution PG, which is what these samples would correspond to, then D of X or sigma of X, which is sigmoid activation function in D, would be equal to 0, which means log of 1 minus D of G of X, in this case would be log of 1 minus sigmoid of X, would be equal to 0. And if you see the graph of log 1 minus sigma of X and the gradient of log 1 minus sigma of X, when log 1 minus sigma of X is 0, obviously the gradient is also 0. So which means you will get a 0 gradient, which means G will not get any gradients to train and will never learn. So training discriminator completely well in the beginning is not going to help us get a good generator, which is the main objective of a GAN. So what do? We want to alternate between training the discriminator and training the generator using objectives O1 and O2 respectively. Let's try to see how this is done in the algorithm for GANs. So the original paper by Goodfellow recommends that we first sample, so for k steps, You first sample a mini batch of m noise samples from the noise prior Pg of z. So remember, we had a Gaussian from which we get a few vectors which we call noise samples. Similarly, we also sample a mini batch of m examples from the original data distribution P data, which is your training data. Now remember, your overall objective is log of d of x plus log of 1 minus d of g of z. And remember that the discriminator wants to maximize both of these. That's what we said so far. And a maximization problem is solved by gradient ascent, just like how a minimization problem is solved by gradient descent. A maximization problem is solved by gradient ascent, where in each iteration you go in the direction of the positive gradient, not the negative gradient the way you did with gradient descent. So we update the discriminator by ascending its stochastic gradient, which is obtained by taking this loss function and differentiating with respect to each weight in the discriminator network. And you do this for k steps. So for k steps, you update the discriminator. It's not yet completely trained. Once you've done it for k steps, now switch over and train the generator. So you sample a mini batch of m noise samples from the noise prior, update the generator now by descending its stochastic gradient, because for the generator we wanted to minimize over the second term in the objective. The first term in the objective anyway did not depend on g, only the second term depended. So we now like to minimize log of 1 minus d of g of z with respect to the parameters in the generator network g. Now this is repeated over training iterations, and this is used to finally come up with a model for the generator. At test time, what do you do? Once you have trained the full model, you can discard the discriminator. You take a sample from your Gaussian, send it through the generator network, and the image that you get is what you're going to assume belongs to your original data distribution. One point here is, what does it mean for such a network to converge? So far, we spoke about whenever we had a loss function, we always wanted to minimize the loss function and wanted to ensure that the loss goes to 0. To avoid overfitting, we perhaps may not let it go to 0, but we at least wanted to see the loss reducing over iterations. However, here we have two components where one is perhaps trying to increase the objective function value, the other is trying to reduce the objective function value. So what does convergence mean for such a network? Let's see that in more detail.